Okay. All right.
Great. Are you ready to get started then?
Yeah.
Okay, fantastic. So thank you everyone for coming to Dummies today. Since the first one was so popular, we've come back with a second edition. And without further ado, I'll give it away to Kai then. And I guess questions throughout as usual, yada yada yada.
Yeah, same as always.
Great.
All right, so I do want to actually finish the notes that I wrote, which is going to be hard. So I'm not going to, I will very briefly review what I talked about last time for those who didn't see it. Okay, so what is a symmetry? Okay, so the general definition was that it could be modulated or unmodulated. It could be a K-form symmetry, where K can range from -1 up to the dimension of space. And it can be invertible or non-invertible. Okay. And an ordinary symmetry is one that is zero form, unmodulated, and invertible. In particular, an ordinary global symmetry is a representation of a group. So I'll just write rep of a group on the Hilbert space. So groups have inverses, which makes them invertible. They act on the entire system, which is what makes them zero form. Their charges are zero dimensional. And they act homogeneously in space, which makes them unmodulated. More generally, there are two requirements for something to be a symmetry, which is that I have some operator that commutes with the Hamiltonian, and that operator is quote unquote topological. So what does it mean for an operator to be topological? In the case of ordinary symmetries, they act on all of space. Being topological doesn't mean anything. In the case of higher form symmetries, they only act on some region of space. So for a one-form symmetry, the symmetry operator would be like a membrane. It's a codimension one operator. And for such an operator to be topological means that I can deform it. So the action of the symmetry operator only depends on the homology class that it is, of the manifold on which it is supported, so to speak. I gave some examples last time. So I talked about ordinary symmetries. We can have like a transverse field Ising model with a Z2 symmetry, which is spontaneously broken. We can have so I'll just draw the picture. So we have some sort of Hamiltonian, which is of the form, or let me just give the general picture. So the general picture here is of what I'll call abelian lattice gauge theory, or abelian lattice field theory, basically. For a K-form G symmetry, where this G is an abelian group. So this is higher form invertible symmetries, described by an abelian group. I have a Hamiltonian, which is sum over all K plus 1 dimensional cells. So I'm going to think about a triangulation of space. You could write down the quantum field theory version, but I don't want to talk about differential forms. So take some discretization of space, take sum over all the K plus 1 dimensional cells, and take the product of some sort of Z operators on all of the K dimensional cells in the boundary. So this is product, and this will have like a minus J, and then some sort of transverse field term that induces some fluctuations. So this is the general picture for higher form abelian symmetries. This describes K-form abelian gauge theory, basically. And the important thing is that in the ordinary case, so we have some symmetry operator, which is going to be the product on some codimension K manifold of the x's, and we have some charged operators, which are the product on some k-dimensional, so these are all closed manifold, k-dimensional closed manifold of the z operators. And because this is codimension k and this is dimension k, that means that these operators will intersect at one point, basically, or at some discrete points. And at those discrete points, they will fail to commute. So this is what it means to have a k-form symmetry. And the general picture then is that I have some symmetry breaking as a function of h over j, such that at small h I have a spontaneously broken phase, and at large h I have a symmetric disordered phase. And in the spontaneous symmetry breaking phase, I'm going to have ground state degeneracy, and I'm going to have, in the case of a continuous symmetry, like U1, I'll get Goldstone mode. In the case of a ordinary symmetry, a continuous, if I spontaneously break a continuous ordinary symmetry, I get Goldstone modes. In the case of higher form symmetries, I get photons. So photons are the Goldstone modes of spontaneously broken continuous higher form symmetries. So there's a restriction here that this G is abelian. So for higher form symmetries, in order to make this term well defined, I need the G to be an abelian group. Because I didn't tell you non-abelian groups, this product is only defined if I give you a path ordering, right? And if I tell you how to order the Z's. But if I don't tell you how to order the Z's, then I can't write down this guy, basically, right?
Sorry, G is the group of what? G is the group
The symmetry group. The symmetry group. So I take some group, and I write down this gauge theory Hamiltonian, basically.
So G is the group of these products of Z? Or?
Yeah, so the idea here would be that the Z eigenstates are the group eigenstates. So this is diagonal in the group basis. This pulls out basically some phase e to the 2 pi n. So for a Zn symmetry, that just pulls out a phase. And then the x operators acting on these states. So let's say this is labeled by n. This is n plus 1. So the x operators are toggling you between these states.
So the cell structure doesn't enter into the group or the symmetry?
No. Yeah, I take any discretization of space and I write down such Hamiltonian. So last time I talked about all of this in more detail, and I was more careful about it. I want to, given time, I want to move and tell you about some new things that maybe are more interesting. So the basic point of this story, however, is in the ordinary symmetry case of an invertible symmetry, a zero form invertible symmetry. We have minimal models like the Ising model or the XY model or some nonlinear sigma model, for example, where you have a global symmetry described by a group and it spontaneously breaks. And basically the Landau tells us that if I spontaneously break some group down to some subgroup H, then I have some ground state manifold, which is basically going to be G mod H. And so I can classify phases in this, classify phases based on how they break their global symmetries. And the basic point here is just to say that I can extend that notion to these higher form symmetries. In particular, I can think about the deconfined and confined phases of lattice gauge theories in terms of symmetry breaking. The confined phase of a gauge theory is the symmetric phase, and the deconfined phase, or what people sometimes call topologically ordered phase, spontaneously breaks a higher form symmetry. And so deconfined phases of gauge theories and topological orders, like in the toric code, for example, these can only be understood within this symmetry breaking paradigm of Landau, basically. So that's kind of the lesson for higher form symmetries. So today I wanted to tell you about something different. I gave two examples last time of modulated symmetries as well. I talked about a clock model, like an unbalanced clock model. So I talked about a Hamiltonian that was like, instead of being like ZZ and X, right? So the general Hamiltonian I'm considering is something like of this form. You can raise this to some power, for example, and then add its Hermitian conjugate. So this becomes, for some Zn, this becomes some unbalanced clock model. And it turns out then that this guy has a symmetry which modulates in space. So I can do clock rotations, but only if I do the rotations such that the first site rotates by a certain amount, and the second one rotates by another amount, and the third one, and so on. So it's still a symmetry, it's a global symmetry, but it's modulated in space. So basically I've covered the idea of higher form symmetry and modulated symmetry. So what I'm going to aim to tell you about now is non-invertible symmetries. And once I've talked about that, I'm going to try to give some examples, some non-trivial examples of where these sorts of symmetries arise and how they how they come about as emergent symmetries. So I want to give myself some. Does anybody want to ask any questions at this point? This was mostly a review of what I talked about last time. Just sip from my beer.
I've heard also using the term immanent symmetries in this context. Is this related as well?
I think this term refers specifically to symmetries that are present in a CFT, a conformal field theory, at a critical point, and whether they are eminent from an underlying symmetry in the UV theory, in the lattice theory. Yeah. So you can have symmetries at the conformal field theory fixed point, which are not symmetries of the underlying model. So these are kind of emergent symmetries. And yeah, so I'll mention something about emergent symmetries. I'm not going to talk about this notion of eminent, but yeah, so there's one example, which is the transverse field Ising model at its critical point. The CFT has a particular symmetry, which is non-invertible, and it's now known that there actually is such a non-invertible symmetry at the UV scale in the lattice model, and so it's an eminent symmetry. But I'm not going to talk about that really. Mark?
You might have mentioned this last time, I've forgotten. What is exactly the notion of a -1 form symmetry?
If a 0 form symmetry is conservation of particle number, a -1 form symmetry is conservation of instanton number.
Okay.
So it's a symmetry that doesn't act on all of space, but all of space-time. I don't know how useful the concept is, but it exists and people mention it from time to time. Some people talk about this in relation to instantons in QCD, for example. I don't know much about it though. But in principle, yeah, you can extend this to -1 by saying that I have a symmetry that acts on all of space-time instead of just all of space. Yeah. Okay. Any more, James?
Oh, I think Kadrubal's first, actually.
So about the underlying gauge group, so is it fine for the underlying gauge group to be non-abelian as well, and the K-form symmetry then should be abelian symmetry?
Well, okay, so you can have the underlying group be non-abelian, but the problem is that these operators will not be well defined, and this is this codimension K, because so when you have a non-abelian gauge theory, there is a one-form symmetry where you have these operators, but they're only labeled by the center of the gauge group, because the center of the gauge group is essentially abelian. It commutes with everything, and therefore I can have well-defined operators like this. So these are basically the electric field operators, if you will. You can think of this as e to the I integral of the electric field through some surface, on some surface. And this would be e to the I integral of this would be your Wilson loop. And this would be your, I don't want to say to Hooft loop, it's not quite the same concept, but then you have this electric field operator thing, where this is some non-contractible surface. So the conserved quantity is this electric field, but these guys don't commute with each other for a non-abelian group. And so, and in particular, like this is not well defined for a non-abelian group, basically, right? So it's only the center of the group that gives you a symmetry in the non-abelian case. There is a notion of having higher form non-abelian symmetries, and that goes into category theory. So you can have higher category symmetries, which are called higher group symmetries. So you have to extend your notion of group to something that allows for multiplication of group elements across surfaces instead of just along strings, for example. And this leads you to the concept of a two group, and then you can generalize that in higher groups, or sometimes called crossed modules. Yeah. But I won't talk about that. Yeah. One more.
Yeah, and I just had a brief question. We can chat about this later as well if it's easier then, but it was just about the fact that once you introduce this notion of a higher form symmetry, I've heard that you can bring sort of these topological class and phase transitions into this Landau paradigm.
Yeah, so the basic example is Z2 gauge theory. Z2 lattice gauge theory has a phase transition. Let's say you're in like 3 dimensions. And the symmetry broken phase, well, from this perspective, it's symmetry breaking phase, is what older work calls topological order phase. For example, the toric code has Z2 topological order, and that can be understood as the spontaneously broken phase of a Z2 symmetry.
Okay.
Another way to think about it is spontaneous symmetry breaking kind of means that your ground state is some sort of coherent state, right? It's a condensate. But for these higher form symmetries, it's not a condensate of particles or a charge condensate. Instead, it's a condensate of higher dimensional objects like strings or membranes. And so condensing strings is what's known as a string net, and that is the standard model for topological order, basically.
Okay, fantastic. Yeah, and that's these anions in sort of the toric codes that do topological.
Yeah.
Okay, yeah, great, thank you.
So everything I'm talking about here is abelian. In principle, maybe this non-invertible symmetry will connect to the anion stuff. So this is kind of like, I think that it is hypothesized, let's say, I don't know clear examples, that anion phases can be spontaneous, like not what are called non-abelian topological phases that have anions that have non-trivial fusion rules, and braiding statistics can be understood as higher form non-invertible symmetry breaking. But anyway, let me move ahead and talk about non-invertible.
Just one final question.
Yeah.
Sorry. So one specific example that is a gauge theory, and when people say physics is not related to symmetry breaking, is, as you mentioned last time, superconductivity.
Yeah.
And an easy way of seeing this is that the excitation, then the Cooper pair in this case, is actually gapped, right? Now you're saying that there is this new way of thinking about it, coming from a higher form symmetry. What would that imply about spectra of excitations, or is this then no longer the relevant thing to look at, or like what does it mean like for the physical objects, you know, the physical excitations, however crazy they might be in terms of strings and whatever loops?
Yeah, I mean, okay. I think it's a hard question. So, well, you mentioned superconductors. I think superconductors are still like an open question as to how to like really categorize these in this picture.
We can do the
Right.
QED if it's easier.
Well, from the perspective of pure gauge theory without matter, then like pure U1 gauge theory, for example, it has a symmetric phase, which is the confined phase, where so your basic excitations are strings of electric field line, basically, and these will cost energy proportional to their length in the confined phase, so they're gapped excitations. And then you have a picture that as you approach the transition, to go into the deconfined phase, you're going to proliferate. So the string tension of these electric field lines is going to go to 0, and then they're going to proliferate and condense in the system. And that we suppose that, like, when we see light that is kind of all over the place, that we're looking at some sort of condensative electric field lines, basically. We live in a condensative electric field lines, or coherent state somehow of this higher form symmetry. And that's the picture of this deconfined phase. And then you have a Goldstone mode, which, if you like, is somehow the transverse vibrations of these strings, and that's the photon that we see, right? Now, when you add matter into the picture, I think the interpretations become much more subtle, because you strictly break the symmetry explicitly, but it's kind of robust in some sense. It becomes emergent at low energies, below the gap of the excitations, and then you find that, right, so I add some, so I have this H over J, and then I have a deconfined phase and a confined phase, and here I'm adding some matter in this direction, some sort of matter field fluctuations, and then I find that the deconfined phase, even though adding this axis explicitly breaks the symmetry, because the conserved quantity is the electric flux. And when I add matter, I get rid of electric flux conservation, right? Because I have sources and sinks of electric flux now. But as long as the matter is gapped, then I still have like a well-defined ground state somehow, which has an emergent higher form symmetry where electric flux is conserved in the ground state, and I still get this deconfined phase somehow. Now, once you go all the way up here into this Higgs phase where you condense the matter, which would be the superconductor, then I think that the interpretation is like very, I don't know how to interpret this. There are other ways to think about this in terms of like boundary symmetries or something like that. But I think that what goes on up here in particular is kind of like a really interesting open question as to how to think of it from a symmetries perspective. Yeah. Okay, so let's talk about non-invertible. So I want to give, so there's two kind of key examples of non-invertible symmetries for a condensed matter audience. One is that the transverse field Ising model has a non-invertible symmetry, but only at its critical point. And effectively, the simple way to understand this is that the transverse field Ising model has Kramer's 1A duality. Kramer's 1A duality switches, so I have a minus J ZZ minus H X. So I have this kind of model, right? And Kramer's 1A duality switches H and J. So it's not a symmetry, it's a duality, right? It maps it maps two different Hamiltonians, two different systems, or classically high temperature to low temperature. Here, large field to low field. However, at the critical point, when here H is equal to J in the transverse field Ising chain, it becomes a symmetry, effectively. But actually, it turns out that it's a non-invertible symmetry. And the reason for that, I'm not going to talk about. It's too complicated. You can look at the work of Shuheng Xiao. So he has some very, very detailed lecture notes on this topic of non-invertible symmetry in the Ising model. And this is one of those eminent.
What is wrong with the naive view that if you do the duality twice, you get back to the original model? If it's non-invertible, it means probably that this idea is too simple, too naive. But
yeah, because
what is wrong?
Because if you look at how it acts on the states, it sends because at low field the ground states are all up and all down. And at high field, it's a superposition of up and down. And so what you actually find is that both of these states under the duality get mapped, they both map to this state. And so it's not invertible. And there's some subtle reason why it's non-invertible, and that's connected to boundary conditions and inserting symmetry defects into the system. I don't have enough intuition to really just pull this out of nowhere and explain this to
So
you. But yeah.
is there an idea that not only you think about a model, but it's possible classes of boundary conditions altogether, and that the symmetry acts on this type of data, not just on the model defined by a sort of local Hamiltonian. You need some more global data that define a set of boundary conditions.
Yeah, I think here in this case, and there are generalizations of this, what are called duality defects, are a common way to generate non-invertible symmetries. It is somehow closely related with boundary conditions and inserting and twisted boundary conditions, basically, and different twisted sectors of your theory. But I'm going to set this entirely aside because I want to show you some more concrete example in a model that is far less abstract and more similar to the sorts of transverse field Ising model and gauge theories that I've been discussing so far, in which you can understand a non-invertible symmetry. But I think this is very interesting, this whole thing, but I don't know a whole lot about it. And I think given the limited time, it'll be more interesting to talk about something more concrete. So my idea here is going to be to generalize this notion. So I've considered all these models written in terms of these sorts of like poly Z and poly X operators, or their generalizations, right? And the generalizations that I've considered really so far have been to abelian groups. The poly Z and the poly X you can think of as being related to a Z2, like in the Ising model. And I can easily generalize poly Z and poly X for a clock model, for example. The eigenstates of Z tell me where I am on the clock. Those are my position eigenstates. And the X operators then toggle me between the different clock states, basically. So they perform my shifts, right? And I can generalize that all the way up to the case of U1, which is like just taking Zn, where n goes to infinity effectively. Then the Z's are going to become e to the I theta. Those are the positions of a rotor. And the X become the angular momentum, e to the I lambda n, which rotates my rotor by an amount lambda, right? Where theta and n are conjugate. So these are all for the abelian case. So the question that I'm going to ask now is, what happens if we try to generalize this to the non-abelian case? And if you do this, then what you get is called G-QDIT model. And the idea is as follows. Consider a 1D chain. And imagine I have a tight binding model on a 1D chain. I have a particle that can hop around. I write down a simplest nearest neighbor tight binding model. That tight binding model has translation symmetry. Having translation symmetry corresponds to having a ZL symmetry, right? Where if I have L sites. On the other hand, I can Fourier transform and my tight binding model, and then I would have some bands of my Hamiltonian, right? A single band. And I could then tune my Hamiltonian to a point where I had a flat band. And once I have a flat band, I have momentum shift symmetry instead of translation symmetry. So I have kind of a notion of a dual symmetry, which in this case would be another ZL symmetry, coming from the, in the case of abelian groups, the Pontryagin dual group, which is another ZL. So for ZL, the Pontryagin dual is ZL. So the idea now is to imagine this. Imagine these sites of my chain as being elements of ZL, of the group ZL. And really I'm thinking of my tight binding model as a particle that's hopping between the group elements. And generalize this idea to a non-abelian group. So now I have some, so imagine I have some non-abelian group which maybe has some sort of I'm just going to draw some arbitrary arrows here, but some Cayley graph, for example, it has a more complicated structure than ZL, where different group elements are related by group multiplication. So I multiply by some group element G, and it takes me from one group element to another. And I could now write down a Hamiltonian for a tight binding model on an arbitrary discrete non-abelian group taken as a set of sites. And I have natural translation operators on this group, where there are natural, the natural group multiplication of the group acting on itself will just permute the sites around. And so it would naturally move my particle from one site to another. So my idea now is to consider some Hilbert space, which is spanned by these states ket G, where G is an element of some discrete non-abelian group. This is called the group algebra, this Hilbert space. And then I have natural quote-unquote translation operators on this space, which are labeled by group elements, such that acting on some state H, this operator does left multiplication. Oops, sorry, GH. So I put the arrow pointing from left to right to indicate that this multiplies from the left. I also have operators that do right multiplication, and it's most convenient to make those H G inverse. And multiply from the right by the inverse. So the idea is now I could write down a Hamiltonian in terms of these operators. That is just like a little tight binding model that hops my particle around between the group elements that would have a G symmetry. The analog of translation symmetry for this problem is to have a G symmetry. And the question then is, what is the dual of the G symmetry? What is the dual symmetry that you get when you go to do some sort of non-abelian Fourier transform and go to this kind of generalized flat band limit in some sense? So I will explain to you basically what that is. And the idea is that I need to define what the appropriate Z operator is here. But it's a little bit unintuitive, or it's not obvious. The idea is that this Z operator, acting on one of these states, this should be my position operator. So in some sense, it should pull out the group element. It should tell me where I am in the group. But this doesn't make sense. An operator should pull out a complex number. So the way to do this is you create one Z operator for each irreducible representation gamma of your group. But an irreducible representation can be more than one dimensional for a non-abelian group, and therefore it has matrix elements. And so I also need some matrix elements here. And then the number that I pull out on the right hand is just this alpha beta matrix element in irrep gamma of this G. You can also think of this then as a matrix of operators that pulls out the group element G in the matrix representation of group element G in irreducible representation gamma.
When you define the set of states, I guess, is this supposed to be like a Hilbert space, or?
Yeah, this is my Hilbert space. Yeah.
So what does it mean to add to those G's, like a G and an H?
To add, well, I mean, I can take formal linear combinations like this. I mean, mathematically, I'm just saying that there's I'm taking the Hilbert space that is freely generated by the group elements. So I just consider those as my basis elements, and then I can take their linear combinations with complex coefficients.
This is not related to any representations of the group.
Not related to any representation of the group. Well, okay, this is a representation of the group, and it's called the regular representation of the group. So in particular, these x left operator, these ones that do the left multiplication, these give you the left regular representation of the group. And the right operators, they give you the right regular representation of the group. And these left and right regular representations are actually important for representation theory because they actually contain all of the irreducible representations of the group, it turns out. That's also true for continuous groups, but it's simplest for for the discrete case, that the left regular representation, for example, it's a decomposable, or it's a reducible representation, and it reduces into all of the irreducible representations, each appearing a number of times equal to its multiplicity, or equal to its dimension, sorry. So the idea is that this is some representation rho, which decomposes into a sum over irreducible representations, each of which appears d gamma times, where d is the dimension of the representation. So a two-dimensional representation appears twice, a three-dimensional representation appears 3 times, and so on. And the dimension of this representation is equal to the size of the group, the number of group elements. And then there's a little bit of magic of representation theory that tells you that actually the that these are the same, that the size of the group is equal to the number of it's equal to the number of representations, each multiplied according to their dimension. So size of the group is equal to the sum over gamma d gamma squared. Yeah, sorry. So I guess each of these appears d gamma, and each of these is gamma dimension. Yeah. So, all right. Okay. Okay. So now the idea is that I take some non-abelian group and I build a little Hilbert space out of it. So I have some states. I have some natural operators that act on these states. And I want to use these as my building blocks. I want to treat each of these as a little qubit. So for example, I could take the simplest non-abelian group, S3, permutations of 3 objects. There are 6 elements of the group, so this is a 6-dimensional Hilbert space. So I want to think of this little Hilbert space as forming a 6-dimensional qubit, right? And then I want to use these guys to build some Hamiltonian that does something interesting. So I'll just write down the Hamiltonian. It looks very much like the Hamiltonians that we've described so far, but it's going to be x left, x right, I plus 1. So this is a 1-dimensional chain. Sum over I, trace of z gamma on site I. So I have a 1D chain now, where each site of my chain is one of these little G qubits. So I have this regular representation of my group at every site. And they're all tied together in this way. So far I wrote all of the Hamiltonians as zz plus x, but this one I'm writing as xx plus z. You could also write down the zz plus x1. And the idea is that this guy has a symmetry. I have this operator, this set of operators, R gamma, 1 for each irreducible representation, which is the trace, I'm going to assume periodic boundaries, product over all the sites, z gamma, where implicitly what I mean by this is that it's like a matrix product operator where I'm taking the product of z's, which carries some indices, some matrix indices, and I'm contracting their matrix indices at nearest neighbor. Right, so one here, one here. These are matrix product operators, so they have some physical legs acting on the Hilbert space, and these horizontal legs are like virtual legs corresponding to these indices alpha and beta. And then I'm going to trace these together around the chain, right? So I go all the way around the chain and then I trace this together. So this guy commutes with this Hamiltonian. In particular, it commutes with this term, obviously. But it commutes with this term because I chose a very particular, here I chose this right multiplication and left multiplication. And the reason it commutes is because I have a basis for my total Hilbert space, which is given by specifying G1, G2, G3. I specify one group element on every site. And then if I act with this operator, then it's going to do G1 stays the same. The second site goes to G2. Let's say I have I'll just use H inverse. This site gets multiplied from the left by H, G3, and so on. Now, when I hit that with this operator, right, this Z gamma pulls out the matrix representation, gamma, alpha 2, beta 2, all right, how do I want to do this? I want to do some alpha beta of G2 H inverse, and then the next one is going to be gamma of beta delta H G3, and then so on, right? So when I act with this operator on this state, and now you see that by the basic properties of representations, this is going to split into basically gamma of G2, gamma of H inverse, gamma of H, and then these two will cancel, gamma of G3, right, and so on. And so I get back the same thing as if I had acted first with this operator and then with this operator. So this commutes with this guy. So this commutes with my Hamiltonian. It satisfies the basic properties of being a symmetry. It acts on my entire system, so it's topological. So the question is, what is the symmetry algebra that these guys give me? For an ordinary symmetry, if I have an ordinary symmetry, invertible, then I would have UG times UH is equal to UGH, right? Because the ordinary symmetry is just a representation of the group acting on my Hilbert space.
Is there any subtlety with making it projective representation, or you just allow some things?
Yeah, well, projective representations are not symmetries, but symmetries can be realized projectively on the ground state. But being a projective representation on the Hilbert space is not really the same as having a symmetry. But however, there's lots of interesting stuff about projective representations and SPTs. But let me just show you very quickly that if the group is non-abelian, these operators are not unitary and they're non-invertible. There are a set of states which they will annihilate. So in particular, I can look at the character table of a group. So for example, take the group S3. S3 can be thought of as the symmetries of a triangle. So I have a triangle, and I have 3 mirror planes, and I have two 3-fold rotations. So the character table looks like I have the identity, I have 2 C3s, and I have 3 reflections. And the irreducible representations, I have an A1, I have an A2, and I have an E. This is the trivial representation, this is the sign representation, and this E representation is something that happens only because I have a non-abelian group. Because I have a non-abelian group, it has irreducible representations that have more than 1 dimension. So the E irreducible representation is 2-dimensional, so I've got a 2 here. And it actually has a 0 here. And this 0 is very important. In fact, you can show that for any non-abelian group, any irreducible representation that is greater than 1-dimensional, there always will be a 0 here. And in particular, what that means is that if I act with this R gamma on any state G1,
How do I read this table?
how do you read this table?
Yeah, how do I read this table?
These are conjugacy classes of the group. These are irreducible representations of the group.
And the numbers?
The numbers are the characters. That's the trace of the matrix representation.
Okay.
Sorry. So the trivial representation is every element is represented as just the number 1,
Yep.
and they just multiply.
Yeah.
The sign representation is every element is represented by the number 1 with -1s for symmetries that don't preserve orientation, basically.
Mm-hmm.
But now this is a non-trivial representation. What is this one? In terms of the triangle, it's a 2-dimensional rotation representation, right?
Okay.
S3 is the permutation of 3 objects, but that's the same as the symmetries of a triangle.
Yeah.
So this E representation is precisely the it's the two-dimensional rotation representation. I could write down two-dimensional rotation and reflection matrices, right, representing identity and C3 rotations and sigma v, right? These numbers are then the traces of those. So in particular, you can see that the reflection that sends x to minus x would be -1, 1, right? And so this has trace 0.
Right.
So there's a 0 here.
Okay.
So what happens if I act with this on some state, right? Well, this is simply going to be equal to, by the basic product representation properties, this is the character, so these are the characters, right? This is the character in irrep gamma of the product of G1 through GL, of all the G's in my chain in order, right? So for any state of my chain, which is, I'm just give some product state where I say, okay, G1 through GL on each site. If the product of all of those is a reflection, here it has character 0, and then this state will be then annihilated by this operator. So this R gamma is a projection operator in some, or well, it's not a projection, but it's proportional to a projection. So on the subset of states whose product is a reflection, it acts as 0, and on all other states it can do something else. So if the product is the identity, its eigenvalue is 2, and if the product is a C3 rotation, it gives it -1.
Sorry, maybe there is a missing vector of the chi gamma.
A what?
There is the vector, like it brings out the vector. An operator acting on a state is.
No, I mean this is the trace of the product G1 gamma of G2 gamma of GL, right? So these gammas are matrices.
No,
I'm doing matrix multiplication.
Like
Yeah,
R
but
gamma is an
C
operator.
is diagonal, so if you're right, it's I guess R gamma is a
Oh,
diagonal
I'm sorry,
operator, so yes.
Ah,
Yeah. So it pulls out something, right?
and why did you write before ordinary invertible? What was it referred to? Sorry.
Oh, so this is the non-invertible case. So for an ordinary invertible, so the question now is, what is the multiplication of the R gammas? And I will just tell you the answer. If I take the product of two R gammas, let me write it somewhere else. Maybe I'll go back over here. Then R gamma A times R gamma B is equal to a sum over C, N, A, B, C, R gamma C, where these are integers, so these are 0, 1, 2, etc. Where gamma A tensor gamma B is equal to the sum N, A, B, C, gamma C. So the tensor product of two representations is generically reducible, and it will reduce into some sum of irreps. And in particular, because this product of operators does not itself, so here I take a product and I get a single operator, but here I take a product and I get a sum of operators. And that means that this is not a representation of a group. So they form an algebra, but they don't form a group. And so these are symmetries of my Hamiltonian, but they're non-invertible symmetries. Not whereas a group symmetry is always invertible, because I can always take the UH inverse off of this, for example, right?
What is kept is that the tensor product is associative, so you get something that
True.
is reminiscent of at least part
Yeah,
of
yeah.
the property defining a group. I guess.
Right. Yeah, so it's associative, but there's identity, but because there's a trivial representation, so there's identity, but there's no inverse. So this is called a non-invertible rep G symmetry. So for any non-abelian group, you can get this sort of rep G symmetry, and in fact they occur kind of generically as the dual symmetries of, like, for example, the non-abelian Kramers-Wannier duality would map a system with G symmetry to a system with rep G symmetry. So they occur as the duals of non-abelian symmetries. They can also be higher form symmetries, but I mean, what I like about these G-qubit models is that they act on local qubits.
Maybe I'm not allowed to ask this question here, but is there any physical system that realizes any of this?
I don't know right now, yeah. That's a good question. I mean, yeah, I'm thinking
Is there
about
any
this.
hopes?
Yeah.
I will just do the standard, maybe cold atoms, Rydberg, I don't know. You know, so the smallest non-abelian group is, yeah, I mean, non-abelian symmetries you can have.
So you can write down the Hamiltonians explicitly, right, for.
Yeah, I mean, this is just a simple like transverse field. So the idea now is that this Hamiltonian has some phase diagram where there's a symmetric phase and there's some spontaneous symmetry broken phase where the ground state degeneracy is equal to the number of irreps. So ground states are labeled by irreducible representations, and there's one for each irrep. So if you want to know more about G-qubit models, I'll throw up a quick reference, which is
I guess in principle you could write this down in terms of either tag binding or spinning line. It will look horrible, but.
you can always write down a discrete non-abelian group in terms of clock and shift operators. They're always realized as a subgroup of a product of abelian groups. So in principle, you can use like a clock, like multiple clock qubits and write down such such multiplication operators. But I don't think this is probably not the most straightforward way to actually do this. Yeah, I'll just throw references 2409, 18113. And 2312, 0922. So if you're interested more about G-qubits, you can check out these papers.
For these, when will it be the case that R gamma is realized as some matrix product operator? Is it always the case that it's realized as some matrix product operator?
Well, here in the 1D case, it's definitely matrix product, and then you could try to generalize that with tensor operators somehow to higher dimension. It's not super straightforward. They also can occur in non-abelian gauge theory in some limits, but
If I
And if I try to do a duality transformation, do I get a gauge theory based on group G then, because sites are replaced by links, and it's tempting to
yes.
imagine that there will be group elements on links,
There will be group elements on links, and there will be a symmetry associated to them, which is precisely this kind of symmetry. So they do, this occurs as a, if you gauge a G symmetry, you get a rep G symmetry. Yeah. That's described in one of these. Okay, so it's almost 6, but I wanted to give a couple interesting comments about, so this is my favorite example of a non-invertible symmetry that I think is kind of the most intuitive. If you want to learn more about them, then well, come to the Journal Club, because we'll be talking more about this starting this week.
is there always a tensor category behind the non-invertible symmetry? Because here, well, actually, it looks like the fusion rule of a tensor category, and is it sort of
I don't know
automatically, and then conversely, if you have a fusion category with these rules, can you cook up a model? Suppose you don't have a silly rep G, but
it's not clear to me that any, well, yeah, I mean, I suppose you could probably always cook up some sort of model, not obvious how.
yeah.
But, you know, I mean, if you look at John McGreevy's paper, for example, he mentions that in principle you can view any representation of an algebra acting on your Hilbert space as a symmetry. But, yeah, I don't know the full extent of how to think about this.
In some sense, well, is it an obvious task from rep G? Suppose you know, for example, the number of representations, the fusion rules.
Mhm.
Is there an algorithm to reconstruct the group from this data? Because
Okay, well, there is one case which is in one dimension. Okay, so there are these anion chain models you may be familiar with. So you take an input fusion category and then you can produce models that have that fusion category as their symmetries. That works in 1D. So Paul Findlay did all this stuff. And in principle, there's some extensions of this to 2D as well. So the Kitaev model arises in this way also. You can understand it as you take the Ising fusion category on a particular trivalent graph related to the honeycomb structure, and then you can get the Ising model as the anion model. And then you get these higher form non-invertible symmetries and so on. But I don't know a whole lot about this. Okay, anyway, we're already at 6 o'clock, but I don't want to extend this to a third one, so I will take another couple of minutes. I just wanted to mention, so I talked so far about the notion that you can have higher form symmetries, and you can have modulated symmetries, and you can have non-invertible symmetries. But I just wanted to mention now that actually these symmetries can emerge, they can be emergent symmetries in common contexts. In particular, like rep G symmetries, one way to get them is to gauge a G symmetry. But what does gauging mean? Well, gauging is a method of generating dualities. So they arise as dual symmetries of non-abelian symmetries. And there's this notion of dual symmetries, which is quite important and quite interesting to think about. In the ordered phase, you can have emergent symmetries. So Kramer's 1A duality maps the high temperature to the low temperature phase of a transverse Ising model, for example. And in the low temperature phase, so in the original transverse Ising model, you have a Z2 symmetry. It's unbroken in the high temperature phase, or the high field phase, and it's broken in the low field phase. Kramer's 1A duality says I can map that to a system where I flip this upside down. There's another symmetry, in some sense, that is the dual symmetry, which is unbroken in the low field phase and is broken in the high field phase, right? So there's this notion of having like disorder operators, basically, and there can be symmetries associated to disorder operators, such that you have two symmetries that are dual. When one is broken, the other is not, and vice versa, right? They're never broken at the same time. So I wanted to just mention a couple of examples of emergent generalized symmetries. And in particular, so the first example is basically if so the main reference here is going to be, okay, I don't have it written down. You can check out this paper by Salvatore Pace. It's a single author paper where he wrote about emergent generalized symmetries in ordered phases. So the idea is basically this. Imagine that you have an Ising model. Let's say a classical Ising model in 2D. It has a global Z2 symmetry. It's an ordinary zero form Z2 symmetry. And it is spontaneously broken at low temperature. Now in the ground state, I have excitations, which are strings. They're domain walls. And so you may think, and you can make this more precise, through this gauging, that there is an associated symmetry which is sort of violated by the presence of these domain walls, by thinking of these domain walls as being the excitations of some gauge theory, effectively. And so the idea is that if I spontaneous symmetry breaking of a K-form symmetry, let's say a discrete invertible for concreteness symmetry, gives you a emergent low energy it will be a D minus K form symmetry. So So one way that you could do this is in a Z2 symmetry in the Ising model. And the other is Z2 one-form symmetry. This is the electric symmetry in the Z2 lattice gauge theory. So lattice gauge theory. So I'll focus on the lattice gauge theory for a second. So the idea is that in a lattice gauge theory, I have these Wilson loop operators, which are like e to the I integral of A around a closed loop. Or in the Z2 case, I have some product of Z's on some loops, or on some links going around some loop in my lattice. Now, my Hamiltonian is sum over plaquettes, product over links in the boundary of a plaquette of Z's, and then some over links X operators, like this. So, in general, this object, this Wilson loop object, which is product of Z's around a closed loop, this doesn't commute with the Hamiltonian, and it's not a symmetry. However, it becomes a symmetry if I took H to 0. Taking H to 0 means I go into the symmetry broken phase. So this guy kind of trivially commutes with the Hamiltonian in this limit. And the idea is that you can think that there is an emergent D-1 form symmetry in the limit that H is much less than J, quote unquote. So when I send H to 0, there really is seemingly this higher form symmetry in the sense that I have these like higher form objects that commute with the Hamiltonian. Now when I turn H on, I've explicitly broken that symmetry by the presence of this term which doesn't commute with that guy. However, I mentioned last time that higher form symmetries are kind of, as long as they're higher form, they're robust in a certain sense to spontaneous symmetry breaking. To explicit symmetry breaking. So explicitly breaking a higher form symmetry with local terms kind of doesn't destroy them because they become emergent at energies below the gap of the excitation. So as long as I have a phase that has gapped excitations, then there will be some sort of emergent symmetry that comes about at energies below the gap, and in particular in the ground state. And I will give you another example, which is in a superfluid. Yeah, unfortunately, I'm sorry, I don't have enough time to explain things very nicely, but I just wanted to communicate the basic idea. In a superfluid, I spontaneously break a U1 symmetry, right? A global U1, ordinary U1 symmetry. Now, by this argument, you might think, well, then there should be a corresponding D-form symmetry that is emergent at low energy. But that doesn't happen. Why? Because a superfluid is gapless. It has a gapless excitation, and so this D-form symmetry, which would basically be, so let's think of an Ising model for a second. So Ising, zero form, Z2. I go into the spontaneous symmetry broken phase, and all of my spins point up, right? The excitations out of this are I flip some spins and I create domain walls. And if I'm in a high enough dimension, then these domain walls will be confined. So they're gapped excitations and they're confined. So in a certain sense, there's a Z2 D-form symmetry, which is sort of the conservation of the global Z2 sector in a certain sense. But it's explicitly violated by the presence of these gapped excitations. Now in the superfluid case, I don't get a D-form symmetry because the excitations are gapless. So the analog would be that I have a coherent phase and that this is kind of like, in some sense, robust at low energy. But that's not true. In a superfluid, the phase can just continuously deform over space, right? So there's really no conservation at any finite energy of the overall direction of the phase. However, there is another emergent symmetry which comes from the fact that the group U1 supports homotopy defects. In particular, it supports vortices. So if I have a system like in an annulus where the phase winds, then there's a corresponding, so this is a 2D system here. There is a corresponding one-form symmetry here, which is the conservation of winding number. So for this continuous group, I actually got a, not a D-form symmetry, but a D-1 form symmetry. So in the case of 2D, it's a one-form symmetry. And what this tells me is basically that there's a symmetry associated to the stability of the global winding number of the phase of the superfluid. This global winding number is conserved and well-defined unless I have vortices. If I forbid vortices, this is a real symmetry. If I create a vortex, then I allow this string to end because now the superfluid phase can wind around the endpoints of the string, right? Like this. So I create a pair of vortices, which are like matter excitations in a gauge theory, basically. And so these excitations explicitly break this higher form symmetry, but as long as those excitations are gapped, once again, I can think of having this higher form symmetry in some kind of robust way. So my point is just to communicate that there's another way of thinking about these symmetries as being emergent higher form symmetries in ordered phases. And in particular, the interesting examples are the ones that come from the homotopy groups of your symmetry group. So when you have a continuous symmetry with a non-trivial homotopy group. So I don't want to take any more time, it's already after 6, but there is much more interesting things to say about how to think about these symmetries from a gauge theory perspective. And maybe I can sketch for the example of the U1 how this works. And this goes under the name of villainization. So villainization is a way to see that you really do have these higher form symmetries by turning these theories into gauge theories, basically. So the idea would be, for example, start from an XY model. So my Hamiltonian is going to be like sum over nearest neighbors, cosine theta I minus theta j, theta minus j, and then some transverse field term like n squared, something like this. So this is the angular momentum squared, and the thetas are the rotor angles. Now, this guy supports vortices in the form that I can go around a plaquette, if you like. And if I think of this as grad theta, then on each of these I have grad theta, grad theta, grad theta, grad theta. And I go around a plaquette, and I have curl of grad theta around the plaquette. Now, curl of grad is always 0, right? However, in this case, it only has to be 0 mod 2 pi. So actually, this can be equal to 2 pi times an integer. So I can have vortices because of the non-trivial homotopy of U1. So one way to see this is to do villainization, which is to write down another theory, which is very closely related to this one, but makes these vortices manifest. And the idea is that you can unwind the homotopy groups by adding gauge fields. By representing U1, so by representing U1 as a quotient R mod 2 pi Z, I can replace my rotors with some non-compact variables if I add an integer valued gauge field that takes care of the winding numbers. And so here I wrote a Hamiltonian. I'm just going to write an action for simplicity, just because then I don't have to worry about these terms. And so the action that I'm going to write is minus j, sum over I, cosine. Now I'm going to have phi I minus phi j plus 2 pi mij. So the idea now is that, so now what I'm doing is I'm saying that I'm replacing my thetas with a non-compact variable that cannot wind, but I'm adding a one form, so my thetas are 0 form, they sit on the sites. I'm adding a 1 form gauge field that is integer valued that sits on the links, such that this winding curl grad theta being non-zero is going to be captured in the curl of this gauge field M that I'm adding here into the theory. So now I'm going to add a term, which is going to be like minus G sum over plaquettes, and then this is going to be basically curl of M squared. So now I'm adding explicitly a fugacity term, if you like, for the vortices into the theory. So villainization is a way to take a theory where I don't have control over the homotopy defects. They're there, they're in the path integral, they come with some entropic weight, I don't have any control over that, and write a theory where I do have control. So in some parameter range where I tune this G correctly, this action, this theory, describes the same physics as this theory. It's a theory of some continuous variable that can continuously rotate, plus some homotopy defects, the vortices. Now the idea is that if I take the limit where G goes to infinity, so I make the, we need a plus sign? No, then, so basically the idea is if I go to the limit where I make my vortices infinitely costly, then I will have an emergent, in this gauge theory now, D minus 1 form, Z symmetry in a particular limit now of the villainized theory. So the villainized theory has a genuine higher form symmetry when I go into a particular limit. And so this is just to convince you that villainization is a way of making certain emergent higher form symmetries in ordered phases more explicit. And you can extend this method, I'll stop here, but you can extend this method to more complicated cases. For example, to nonlinear sigma models with a more complex target space. That's not just U1, something like the nonlinear sigma model that describes a ferromagnet, for example, has target space S2, which has a second non-trivial homotopy group. Or you can have nonlinear sigma model with target space the real projective plane, which describes pneumatic fluids, for example. These are manifolds that have non-trivial topology, and they can host non-trivial topological, or I should say, non-trivial homotopy defects. So the order parameter field, if you like, can wind non-trivially. And so the theory, the low energy theory in the ordered phase, in the spontaneously symmetry broken phase, which is the phase where these homotopy defects are stable excitations, has genuine emergent symmetries whose symmetry charges effectively are the homotopy defects. And so by going to certain limits of these phases, you can actually break these emergent symmetries and get new phases in this way. So this is something that is discussed in Salvatore Pace's papers, and if you look at his work with Xiaogang Wen, for example. And you can get, in particular, something even more complicated, which is that if you try to go beyond the second homotopy group, so here I did the first homotopy group, you can do this for the second homotopy group as well. So in particular, this happens with the pneumatic example. So I'll just give the example really quick and then I'll finish. So in the case of a pneumatic, you have something like a nonlinear sigma model with target space RP2. It has pi1 of RP2 is Z2, and pi2 of RP2 is Z. And so it supports, in three spatial dimensions, it will support string excitations, vortex strings, as well as coming from here, as well as vortex particles coming from here. And the vortex strings can terminate on the particles. This is very non-trivial to actually see, but in principle it can happen. And in particular, they talk to each other in a very non-trivial way that is captured by a higher group structure. I won't explain how, but you can go through a similar villainization procedure by representing RP2 as S2 mod Z2. So I replace my zero form RP2 field with a S2 field and a Z2 gauge field. And then this trivializes the first homotopy group. Now I need to trivialize the second homotopy group. So I'm going to represent this as SU2 mod U1 for the S2 component, mod Z2. So now I'm going to have, this was a 0 form field, and I'm going to have to add a 1 form gauge field. Now this was 0 form. I'm now also going to add a 1 form U1 field, and this is 1 form. And now this U1 has a non-zero Z homotopy, which is carried in here. And so I can represent this furthermore by breaking down the U1. Now I have SU2 mod R mod 2 pi Z, just like in the first Villain example, mod Z2. So it's a very complicated way of unwrapping the homotopy groups into things that are trivial. So I have Z and I have Z2 gauge fields now, where this, and I have an R gauge field, I have a Z2 gauge field, and I have a Z2 form gauge field. This one was 1 form, this one is 1 form. But because of the complicated, if you like, fibration of this, this is a sequence of fiber bundles effectively, of breaking down RP2 into a sequence of fiber bundles. But because of the non-trivial structure of this fiber bundle, and the fact that you've unwrapped this into 0 form and 1 form and 2 form, what you find is that all of these gauge fields that you wind up with talk to each other non-trivially. And in particular, the gauge transformations of the 2 form gauge field will be twisted by the gauge transformations of the 1 form gauge field. And what this encodes is the fact that in a pneumatic fluid, actually you have vortex strings and you have vortex point defects. The strings can end on the point defects, and they talk to each other in a very non-trivial way. And this is captured in this emergent higher symmetry through this villainization process in terms of higher form symmetries that have to be packaged together into a higher category called the symmetry category of the problem. So again, you can look at Salvatore Pace's paper for examples of that. And I will end there. Sorry. All right.
Well, yeah, thank you very much, Kai. I think since we've gone over a little bit in time and we've had lots of questions already, we can end it here. And thank you everyone very much for coming, and have a good weekend.